Hello, everyone. My name is Eric Ilio from University of North Carolina at Chapel Hill. Thank you for coming and thank you for choosing this session over the World Cup final. I wish I could tell you the current score, but I consistently get it's 0-0. Okay, great. So my title is Efficient Genome Ancestry Inference in Complex Pedigrees with Inbreeding. So let's start from this cute picture. This is a laboratory mouse. It's an example of model organisms. In many genetic studies, we don't use human. We use this model organism. There are many reasons behind. I guess maybe you can tell more than me, more than I do. So these model organisms are often bred or crossed in the laboratory. They are raised in the laboratory in order to study the genetic influences. So there are organism resources generated using prescribed breeding systems. Some examples are like the all-bred stocks and the recent collaborative cross project, which is a joint effort of several national laboratories and UNC. So here on the right you can see the breeding design of collaborative cross. It starts from 8 genetically different founder mice, and then you see a funnel-like breeding design. It starts with 2 generations of crossing, then followed by a lot of breeding generations. So this breeding system, they use certain design to ensure properties such as diversity and reproducibility. This structure of generations. One thing those worth mentioning is that usually small set of animals from human population starting. So here I would like to use the ancestry. So given breeding, so you can see the DNA sequences mixed in each generation through recombination. The DNA sequence of any descendant is a mosaic of its founder's DNA. Here is a recut mosaic, or in other words, we were over resulting from which founder. So in the book, we use SNP data. This is because with species and vast majority of these mutations are actually due to single base pair new mutations. These mutations are going to nuclear polymorphism or SNPs. Efficient way to get the variance here. Is first some basic background information of the SNP alleles on the same chromosome constitutes a haplotype. High throughput technology do not read haplotypes directly. So reading is obtained at each site. That is an unordered pair, which means you only know the combination of them, but you don't know which one from type. So here shows an example of this concept. These are a pair of chromosomes and their DNA sequences are listed. By the 2 columns are the SNP sites. If we take the nuclear value on these SNP sites, we can get. However, we can read the 2 haplets directly. For example, on the first side and the third side, we both get a combination of TA, but I don't know whether it's TA or AT. Using SNPs to resolve the genome, we're getting the SNP genomes of founder animals and descendant, and we would like to infer the source of each site for each descendant. For example, the first site is a combination of T and A allele. We would like to tell T is from which founder and A is from which founder. So the challenge here is our efficiency, because to achieve very high resolution, there are markers on single cell, and there are a lot of animals. So take collaborative, for example, there are more than 1,000 lines on the 23 generation. There are and most siblings per generation. So I will start from the rendering algorithm. Important method here actually is one of the most widely used pedigree analysis algorithm is to incorporate the pedigree into the Markov model states. The idea of validity is model recombination. Using, I give a simple example to show this haplotype is derived from two parental haplotypes. Version can be viewed at each side as a two-choose later. So we can take a look at the picture on the bottom. Two haplotypes in the child haplotype indicate the serotype either on the left parameter, and you can see a combination of the type. So indicator pointing to the right side is point out the inheritance indicators are plotted. So the combination event here is model indicator of the chromosomes. So if given a pedigree at each snapshot, we need to use two inheritance indicators featured in the pedigree because there are two alleles for each individual. I'm talking about the inheritance is basically the combination of all the inheritance indicators. So any addition of an inheritance vector determine inheritance configuration. So here is an example. The inheritance vector here determines the inheritance flows from founder to everybody in the pedigree. So the anagram take each value of the vector and consider this as a possible hidden Markov model state. And transition in states simply represent combinations in pedigree. There are two neighboring sites and their configurations. So because there is a change in the inheritance transitions, so we can see so it's represented by transition in state, the hidden Markov model. So in constant speed-up method approach to accelerate the computation of the computer still grows exponentially with the number of animals. So it's still capable at solving animal resource. As I mentioned, there are a lot of generations and complex size is too big. So for example, to infer a mouse at collaborated cross with 1K markers, this could indicate like computations in team computation. So observation is that there are several commonly used substructures in the breeding scheme, and from this breeding scheme, these substructures are repetitively used. For example, inbreeding, backcrossing, outcrossing. Although these substructures efficiently if a generic efficient not possible. Our first choice is inbreeding. So the inbreeding here is sibling mating for many generations, and it's genetically reproducible descendants. This is an animal resources because you want to make sure it's reproducible. We choose inbreeding also because inbreeding is usually carried out for management of the computations, and the symmetric structure is for acceleration. So how do you use it here? Let's look at on the right an example of reading, and you can snapshot at any site. On the left, it shows model in random algorithm for inbreeding process. So in there are two siblings. Actually, there are two animals in the beginning. So there are 4 alleles in the beginning of the process. This because of the symmetric structure, they actually have the ability to be passed to the resulting animal. So how about indicators for the breeding process? but the resulting alleles, they are not independent. So we need between them because they share the inheritance history until the last genome. So to model the dependency between them, they are transitions. So the high level idea of work is as an indicator to encode all the information. So we investigate all the possible transitions of this aggregate. We break down into different types of for this type for different events. Enough, which is true for genotyping technology. So derived transition properties of inbreeding. So because we derive many to typical examples. On the left, a single transition has two correlates. So the probability goes up, and then it's generation. This is consistent with our intuition that growth with number of growth generation, but later is highly dependent, and the single the rare. We can see that the paired transition becomes later generation. So we already derived indicator can be incorporated into the Landau green fragmentation. We now have a fast and accurate method to solve the large inbreeding process. So remember just now I mentioned marker U to the 55 for generation 12. Now we can use to the power 23 for mousing arbitrary number 6 regardless of the inbreeding. We conduct our experiments on data and implement our algorithm in C++ across a name of our programming scan. We evaluate with both serial and cross genotype data. So we compare with Happy. First is Happy. Happy is a analysis framework. It also of the genome ancestry. It uses efficient hidden Markov model, but because the breeding scheme information, so the state space is very small, so it's kind of up here. We will compare our algorithm with Merlin, is probably the most widely used Landau green implementation, the sparse tree to accelerate the computation. So let's run first round 3 algorithms simulate data. And the easy way to know the way to evaluate the algorithm because we know the ground truth. We know what, so we can easily examine the misassigned founder. The best ancestry estimated here is correct or not. Both Merlin and again we are incorporated. They are they show very low error rate. Most in estimating the founder ancestry. Very happy have a 20% error rate here. We also made robustness to gender noise, which is a genotyping error here. And the rate of both in and Merlin doesn't change very much. We conduct experiments on real data, but the problem is we don't know the real founder ancestry here. So we can only compare the results. So when happy, they are highly consistent results on generations that processed by Merlin. That means the early generation, because when the generation number of generation big, Merlin can know it. And the results from the Merlin log, which are the founder assignments, the two algorithms very similar, actually almost identical results. Another example, again, we see very similar results. Actually, we see results of all the experiments we conducted. Further, compare our method with happy because, as I mentioned, collaborative cross, like you have to each line on at least 23 generation, but Merlin can handle like at most to 5 or 6 generations. So we have a lot of mice. After that, we have like right now we have mice from I think at the most 15 generations. So we compare our method to happy, which does consider the pedigree information. We reason that incoming pedigree knowledge made a difference between the two algorithms. Start simple here. Any pedigree pair can serve as entry. For example, the founder pair one, the generation image after founder pair you see here never reappear in later genetic material passed from generation 1 animal is generation. So for example here, you should never see this pair as a if any ability is assigned, it must be wrongly assigned. So without considering the probability to the invalid ancestry choices, it shows the analysis result for shaped mouse. Each color represents, and so you can see there is a lot of ambiguity in the best ancestry inferred by many due to that wrongly assigned probabilities, as we see on the right. To conclude the difference between gain and happy, by incorporating pedigree knowledge, we avoid assigning probabilities choices, and this significantly reduces ambiguity. And we made error in Markov model due to wrongly assigned probabilities directly observed. For example, the transition probabilities. We consider some and to like the transition. Some are favored, some transition and not. Either they are equally likely. So, the last thing I want to share is about the rounding time. So this is most actually the motivation of our work. We want to analyze mouse from a very big pedigree. That our algorithm can finish analyzing mouse from in collaborative cross in just seconds. If you know it provides accurate result. The running time with a number of generation, and after the 4th generation, it could take like to process a single chromosome. Happy is faster than our algorithm. You really can't tell the difference between like seconds. But the problem we of happy we have already mentioned. So we have currently used the method in thousands of cross mice, and there are more extracted experiments on sibling studies that show that our algorithm actually provides results. Certain ancestry information are currently used in effect. So to conclude this presentation, animal resources are very powerful tools, can be challenging. It's challenging. It's different from human populations because the pedigree here normally consists of many generations. But you have maybe few generations will improve. So this is different kind of. So MS is not a generic remedy to, but the computation can be crucial for existing models like for collaborative cross. So the insight here is you cannot find a solution to all type issues. Structure modeling handling specific type of future, trying to investigate other use substructure to handle more types of results. I'd like to acknowledge the UNC computational and Professor Wang and Leonard McMillan. I would also like to thank NSF and NIH for providing grant. Also ISCB and Department of Energy for fellowship. And that's all. Thank you.
That most things happen through a single morphism, so it's through single bit. But actually, at least in wild populations, the most common mutation that's inherited so the short tandem repeat rather than the data. So the microsite are a lot more information for pedigree inference than SNPs. Considered how the method would be applicable for non-model. A lot of what usually assumptions that you're making are in human populations and reading with a large family.
Well, what I would say is that actually, I'm not saying that way. I'm not that SNP you can capture all variants. It's accurate enough to solve the ancestry here because enough resolution. But I'm sure if you incorporate more, you can other they can achieve.
Sorry,
did I understand correctly?
No, the question was what you've done for SNPs is applicable for other types of markers. Relations might be the right markers, not SNPs. Okay. Information dies.
So you mean whether our
to multi-allelic, yes. Not to biallelic both, but to multi.
The major assumption I made here is markers are dense enough, so if as you provide a density and they distributed like all the from the.
Hi, I have a question. You mentioned the time complexity of 2 power 23, right?
Right.
In your experiment, the running time is somehow like a constant.
The time of 3 is a constant.
But what is here?
There is no hour of 23.
Oh, okay. The second is you say you incorporate pedigree information. So what could you mean exactly what is pedigree information?
This is actually starting from the pedigree algorithm. I will get how to encode pedigree information into the Markov model. So we start. So this is a very small pedigree. So you start from 4 found end up with 1 resulting animal, and this structure is converted into states in the hidden Markov model. And transition in the hidden model would present the recombinations in the pedigree. So this is how we link pedigree information into a hidden.
So basically, you incorporate the pedigree structure. You yield the pedigree structure, right?
Yeah.
So one more. What if there's a error in the pedigree, kind of incompatibility of
genotyping error
or an error in the mice actually followed? Could you detect that with your method? Low probability.
No, if it is genotyping error, it can be easily incorporated by setting the emission Markov model. If it is we have wrongly labeled or father of an animal, actually can be detected. Because due to the pedigree constraint, you would generate like very mosaic structure. For example, very tiny small pieces of trigger in this number of generation. Actually, we have done a lot of studies like this.